In this video, we're going to focus in on reactions of benzene, and in particular, we're going to look at halogenation. Now, I've drawn here a year 12 reaction that you should know about. So you should notice here that my alkene, ethene, reacts with bromine through an electrophilic addition reaction where the bromine adds across the double bond, producing a haloalkane, and in this case 1,2-dibromoethane. Now, benzene will not undergo this type of reaction because of the stability of the benzene ring. Now, you would observe in this reaction that you would have an orangey brown solution here because of the bromine water will turn colourless. That means that this cannot be a test for benzene because bromine will not react with benzene. Benzene will not undergo addition reactions, unlike the alkenes. So let's have a look at how we can actually halogenate benzene, how we can add the bromine, or how we can substitute a bromine onto the benzene ring. Now, taking a look at our bromine first, we'll notice that the bromine is not polarised. They both have the same electronegativity, so it's not a polarised molecule. In order to do that, what we need is to use a catalyst. For this, we're going to use FeBr3. Now, the FeBr3 has an iron in it, and the iron has a 3+ charge. Now, this is a strong positive charge. This is a dense positive charge, which has the effect of drawing the electrons to one end of the bromine molecule. Now, what that ends up doing is polarising the bromine. So the bromine has been polarised because the electrons have been drawn to one end. From that, you end up getting FeBr4-, and the most important part here is the Br+ electrophile. So this has produced the electrophile required to substitute onto the benzene ring. Now, the reaction mechanism is similar to all the reaction mechanisms of benzene. We have our benzene ring here. We have a bromine electrophile with its strong positive charge. We need to show the movement of electrons from the benzene ring, showing that the arrow comes from the ring or within the ring, so it must touch or come from within the ring. There'll be a momentary break in that ring, and we'll have this horseshoe shape with our bromine attached to one of the carbons. So this is a temporary structure where we have a positive charge here where the ring has been broken. Notice that the ring has not been drawn beyond carbons 2 and 6. I've said that the FeBr3 is a catalyst. Now, what we will need to show next is how the FeBr4- removes a hydrogen to reform the FeBr3 catalyst. Now, what happens is the electrons from the bond between the hydrogen and the carbon are drawn back in to reform the benzene ring. The product of this reaction is therefore bromobenzene. The proton was released from this, and this is going to be used to reform the catalyst. In reality, the FeBr4- will actually remove the proton here at this stage. For OCR A-level chemistry, what you need to show is simply how this proton, this hydrogen ion, reacts back with the FeBr4- to reform the catalyst. And that's very, very simple. FeBr4- reacts with the proton to reform the catalyst, and the other product of the reaction, which is HBr. Now, I'll clean this up now, and we'll have a look at the overall reaction for this for this particular halogenation. So that's the mechanism for the reaction. Here is the overall reaction for what's taking place. So we have benzene reacting with bromine. We have an FeBr3 catalyst. We have bromobenzene and hydrogen bromide released. Notice the FeBr3 has been drawn above the arrow because it is a catalyst, it is not a reactant. I hope that's a helpful video. You will need to look at conditions for this reaction. I will make a further video in the future on those conditions, but for the moment this is just to look at the reaction mechanisms.